This video, we are going to do some application problems. I have the calculator ready to help us with some of the calculations if needed. We're going to start off with a population problem here, number 45, and it gives us the equation P is equal to negative 0.0023t cubed plus 0.015 t squared plus 2.83 t plus 281.8, and we're told that t has to be between 0 and 13 inclusive, where t equals 0 is equivalent to the year 2000, and t equals 13 is equivalent to 2013. So we want to make a conjecture about the maximum and minimum populations of the United States from the years 2000 to 2013. Let's go ahead and look at the graph here to help us make that conjecture. 0.0023, and we'll use x here instead of t's, x cubed plus 0.015 x squared plus 2.83 x plus 281.8. And let's see here. Zoom 0 for right now, and going to zoom out. There we go. And window, we want to go from 0 to 13, and y is, I'm only interested in the part that is positive here. So let's zoom in a little bit more on that. Y max, let's make it maybe 10,000. I trace this. It looks like my population is going up. As I go to the right, just looking to see if I ever reach a minimum there. That looks like it's going down and staying down, so maybe let's make this go up to only 300. And go by tens, right? So again, want to look at that. That looks to me to be just a steady increase. So that would tell me that my conjecture is that since it appears the population is always increasing, on t is between 0 and 13, the minimum population would be P of 0, and the maximum population would be P of 13. So now we're going to want to prove that to ourselves. So we call analytically, we're going to take the derivative here. So giving myself a little bit of space here. That means P prime is equal to negative 0.0069 t squared plus 0.030 t plus 2.83. We're going to set that equal to 0. And we have a really nasty quadratic equation here, where this is A, B, and C. I'm only interested in t values that are positive here. So A is equal to a negative 0.0069. B is equal to, let's go ahead and flip these signs. Let's multiply everything through by -1 to make A be positive. B will be a negative 0.03, and C will be a negative 2.83. That just makes my life easier. So T is going to be negative B plus or minus the square root of B squared minus 4AC all over 2A. T is equal to, let's figure out what that square root is there. Second square root of 0.03 squared minus 4 times 0.0069 times negative 2.83, and then that's going to be plus 0.03 So we have 0.03 plus or minus 0.2810836.175 over 2 times 0.0069. Let's call this answer here X. We have 0.0 y equals n over d, 0.03 plus x over 2 times 0.0069. We have t is 22.54. Second entry, make this a minus instead of a plus here. And I get negative 18.4 0.19. That doesn't make any sense for a time. That time where I reach my turning point, my maximum, where I'm going up and coming back down, that's way outside my boundary of what I'm interested in between 0 and 13. So I have negative 18.19 something, 22.54 something. And what I'm interested in here between 0 and 13 is in this interval. If I stick in 0, here I get a positive number. So all of this is positive. It's increasing in this interval, just like I thought. So there is a absolute minimum at 0. Going to go ahead and second table 0, and second table, see 13. This is still my original function. So I have when t is 0, p is 281.8. When t is 13, I have 316.07. Those are millions of people, by the way, for my population. And then so maximum population will be 316.07 million people, and my minimum population will be 281.8 million people. They ask us to write a brief paragraph to explain, to compare our conjecture with our results, and the minimum population was about 281.8 million in the year 2000. This is year 2000. These are approximations. The maximum population happened in the year 2013, and it was approximately 316.07 million. Just to tie those two things together, that we said that the minimum should happen in the first year, 2000, and the maximum should happen in the last year. Put them together there to form just a little brief paragraph. All right, let's go ahead and skip number 46. You guys can do that on your own. It's to analyze a graph that is shown there. I'd rather work some problems out and do them on the calculator than analyze pictures that are in the textbook for you. So let's go ahead and look at number 47. And we have a cost function C of 3x plus 20,000 over x. X is between 0 and 200, but x can't include 0 because I'm dividing by 0. So I need to produce more than 0 items, but can produce at most 200 items in this model. So C prime is equal to 3 minus 20,000 over x squared, which is 3x squared minus 20,000 over x squared. And my answer, if I set this equal to 0 for my critical number, will be x squared is equal to 20,000 divided by 3. and x is equal to the square root of 20,000 divided by 3. And I can't have the negative because x has to be between 0 and 200. So let's go ahead and check my endpoints. So root 20,000 divided by 3. Let's check that in the calculator here. So clear is going to be 3x plus 20,000 divided by x. Second table, 0 is an error, can't do that. Square root of 20,000 divided by 3, all inside the square root sign, is that number, and then 200 is this. So I have this is undefined. This is 489.90. These are in dollars. Let's see, are they in thousands of dollars or something like that? Just dollars. So, and then 200 comes out to be 700. And if we go ahead and look at this graph, zoom 0, window, this needs to go from 0 to 200. Cost needs to go from 0 to, let's go with 1,000. Let's go by hundreds here. We can see that it comes to a minimum value here at square root of 2,000 over 3. Right here, it's going to go back up, but it's not going to get as high as where it started off. Over here just can't ever get to 0. So that's really not the absolute maximum over there because it starts off to really high value. But we want to find the minimum cost right here, which we can prove that that's the minimum cost with our first derivative test if we want to, that if we would factor this, we would get, let's see here, we would get 3 times x minus root 20,000 over 3 times x plus root 20,000 over 3 over x squared, and I could put something in that was, let's see what root 20,000 over 3 is. Root 20,000 over 3 is 81 point something, so something bigger than 0 but less than 81.6 might be like 81. So this would be a negative value times a positive value over a positive value would be a negative on that side. Root 2,000 over 3, that's decreasing. On this side, we would get a positive, and a positive. That would be increasing, so there's a local min right here. Local min at root 2,000 over 3. And again, I'm going to find C of root 2,000 over 3. I did that with a calculator here and found it to be approximately 489.90. 89.90. And now I can't produce root 2000 over 3. It's not exactly right, so I'm going to have to round this because it's, like I said, it's 81 0.65. We're going to have to round that up to be about 82. So that's going to be where our minimum cost is going to happen. If I go ahead and look at my calculator, what happens at 81 and 82, just because 81.65 is between the two of them, that I can see that my cost is slightly smaller at 82 than it is at 81. That's why the minimum happens at 81. I'm sorry, at 82. All right, let's go ahead and look now at, let's just, I'll let you do number 48 and I'll do 49 with you. So 49 will be profit. And when soft drinks are sold for $1 a bottle at a football game, approximately 6,000 bottles are sold. So we have 6,000 bottles for $1 for price. This is going to be X and P of X here. And then when we have $1.20 a bottle, we sell 5,600, and the initial cost is 5,000. Initial cost 5,000. So C0 is 5,000, and the cost per unit is 50 cents. So C of X is equal to 5,000 plus 50 cents times X, assuming that the demand function is linear. So that's a good assumption here for us to make, that I can make a line out of this for P, little p of X is equal to, let's see, slope here is going to be let's pick this one. So y minus 1 is equal to m, which is going to be 120 minus 1 over 5,600 minus 6,000 times x minus 6,000 for my equation. So y minus 1 is equal to, this is actually little p, and this is 20 cents divided by negative 400 is math, answer to fraction, negative 1 over 2,000. X minus 6,000. So P is equal to negative 1 over negative X over 2,000 plus 3. I have plus 1. So P is equal to negative x over 2,000 plus 4, which makes my R of x equation equal to 4x minus x squared over 2,000. And then I have my cost function there. So revenue minus cost is going to give me profit. So let's find that. Let's let's see, capital P of x is 4x minus x squared over 2,000 minus my cost function of 5,000 plus 50 cents a bottle is going to give me capital P of x is 350x minus x squared over 2,000 minus 5,000. So dp dx is 350 minus x over 1,000, and then that goes away. We're going to set this equal to 0. And we get negative x over 1,000 is equal to negative 350. Multiply both sides by negative 1,000, and x is equal to 35. Uh, 350. I'm going to move the decimal point 3 times. Let's see, 350 moves it twice. Another one, so 3,500 is my answer there. So then I'm going to want to stick 3,500 back into my price equation to see what I should set my price at to make my demand that. So it's back here with my demand equation. P of 3,500 is going to be equal to negative 3,500 over 2,000 plus 4 is going to be negative 1.75 plus 4 minus 1.75 is 2.25. Should be my price point to maximize my profit. Let's just make sure they're negative 35 divided by 20. Make sure I didn't make a mistake with that. Yeah, negative 1.75 plus 4 is 2.25. So $2.25 is what I will set my price at to maximize my profit for this event. This, I think it was a football game where I want to sell the soft drinks there, and that should give me a maximum profit of you could go ahead and stick that in there, stick your 3,500 in to the profit equation here to see what you would get. But the question was actually what price should you set the bottles at? And that was $2.25. All right, that's it for this video. That's it for this section. We'll come back next time and we'll start to talk about concavity and the second derivative test. I mentioned concavity a little bit already when we were talking about our second derivative test for extrema, but we're going to do a second derivative test for concavity and talk more about what that means and what that tells us. So see you for the next video.